Welcome back. This is Professor Xiao. Just a quick review. Previously, I have talked about several supervised machine learning methods, including k-nearest neighbor algorithm, decision trees, and regression models. In the following weeks of lectures, I will talk about the last supervised machine learning method of this course, the most complex algorithm so far, artificial neural networks. In this week's lecture, I will only focus on the conceptual side of neural network to give a high-level introduction. Note that midterm exam is next week. I will upload another video to briefly review the midterm exam. Stay tuned. Now let's begin today's lecture. Neural network can be used for classification as well as for prediction purposes. It is a supervised model, and it does have a target variable. It tries to find the link between the input variable that you provide to the network and the target variable, and try to find the association between these variables with the target variable in the observations that you feed into the model, and tries to capture the big patterns that may hint at what information might be predictive in terms of the target values. It is, so far in this course, the most complex model, and the complexity is not only because of the computations that go into calculating and deriving the solutions. And let me tell you, there isn't a single solution here, and not in the sense that you might have alternative trees and you can prune the tree to have different results of the model. In some sense that's equivalent, but in another sense, even if you have a tree with the same structure set up, with the model training, and it trains over time, it literally does not stop. It keeps training and training and training, and get to a model that crunches more and more and more data, or crunches the number in a finer and finer way so that it reduces the errors. Ultimately, the errors are never reduced to minimal. The error between prediction and the data will keep being reduced and reduced and shrinked over time when you train the neural network, but it will be long, maybe days even for a simple model and a small data set. The model can keep training for days and it won't converge. It doesn't mean that the model is deficient, but it simply is because there are so much variances in the data that the model can learn. At some point, you know that the model is going to overfit. So it will be far before the model soaks up everything from the data that the model will be optimal. I'll talk about that. So it's a complex model, and it does have a lot of concepts to learn about how the neural network model work. And I'm only talking about fairly simple structured neural network that has a small number of neurons, the fully connected multi-perceptron models. Nodes and links that work somewhat like regression models. If you take them apart, every node accepts inputs from the previous layer. It forward feeds into every node in the subsequent and downstream layer, and every node uses a linear combination of the inputs from the previous layer, and it does a nonlinear transformation, somewhat like a logistic regression, which also does a nonlinear transformation and translates into a value that's in the small range, understood as probabilities in the neural network terms. It further propagates to downstream layers until it hits the output layer. For the simpler version of the neural network model that we focus on here, it's called multi-layered perceptron forward-feeding network that has three distinct types of layers: input layer, hidden layer or layers, and output layer. Other than the input layer, all the other layers has hidden neurons, and the input layer has neurons that are not hidden, but the input data, every variable is observed neuron. And the connections are how the data or information is fed from upstream layers to downstream layers. So here is a typical multi-layer perceptron forward-feeding fully connected neural network. In this example here, there are two hidden layers in the middle. These would be the hidden layer areas. For this example, it shows two hidden layers. By the same logic, you can have three layers. You could have only one layer, as many layers as you desire. This is the input layer. Each node here represents a feature or variable, equivalent terms to describe input data. Altogether, the input layer will include the entire training data set. So if you have 10 input variables, you would typically have 10 nodes in the input layer. Each of the node in the hidden layers is a hidden neuron. And these hidden neurons is quite conceptual. It's not perceptual. They are hidden, they are unobserved, although you can calculate it, but it changes. That's why they are called hidden. You can still specify the number of hidden neurons. The output layer consists of the output neuron that would translate directly into an output prediction. So let's say if the target variable is binary variable, this output layer will output the probability that the target variable will take the value of 1. And if that probability is greater than 0.5, more than 50% of chance that the target variable will be 1, so the prediction will become 1. Typically, if it's a binary classification problem, if target is binary, then the prediction will be 1 or 0, but the output layer will first calculate a probability. It will be between 0 and 1. The probability will take 1 if. So the output layer will first calculate the probability, and based on the cutoff value, prediction would be either 0 or 1. What if it's not binary classification but multi-category predictions? Then it will output as many number of output neurons as there are a number of discrete labels in the target variable. Say if you're predicting whether or not the outcome is one of 3 different possibilities, then you will have 3 different neurons here, each representing one of the label, and the model will output probability that the target variable will take each of the 3 classes, and then the class with the highest probability will become the predicted label here. So that's called topology of the neural network model. You would describe what are the 3 layers: the input, the hidden, and the output layer, and what is the number of actual layers in that component, and what is the number of neurons in that particular layer. For here, the input layer has 6 input neurons. The hidden layers actually have 2 hidden layers. The first hidden layer has 4 hidden neurons, and the second hidden layer has 3 neurons, and the output layer has currently 1 neuron. Each of the lines here is a connection, and so on and so on, is a pathway where information or variance of the training data is input through the layers from one node to another. Each of the connection represents a coefficient, fairly similar to a regression model. This hidden neuron, it takes input from 6 input neurons, and each of the input neuron is multiplied by the coefficient that represents the connection here. And after the linear combination of the 6 input neurons with the 6 slope coefficients, and after some activation transformation, it becomes the value of the first hidden neuron of the first hidden layer. So the information goes from left to right. It goes through a forward, propagation, where the information is flowed through them, and many coefficients here. Each of the line represents a coefficient. You also have a lot of the beta bias coefficients and some other coefficients. Together, these coefficients with the input data X calculates the prediction for the output. Obviously, at the first few rounds of training, these coefficients are not going to be optimized, so the prediction will be far off. The error is calculated. It goes through one round of backward propagation to figure out how to modify these coefficients, because the data will not be modified. Data are given, only the coefficients are being optimized, and it goes through one round to adjust these coefficients to improve the accuracy of the model. And it goes on and on iteratively in order to optimize the coefficients of the model while keeping the entire structure of the topology of the neural network fixed. Neural networks get their name because computer scientists who work on machine learning were trying really hard to try to make computers work similarly as humans, because in those ages, computers are trying to do as well as humans can do. The reason why neural networks have that structure is because human neurons, based on biology, look similar like that. The nerves will collect information, will feed back into the central neural system to process the information and feed back to react to the world. The reason that the nodes are called nodes is also because of these terminologies in neuroscience and biology. This describes the two process of forward. You have the linear combination, calculates sigma, and through an activation function, it translates into a value of y that is very small, that imitates probability terms. Later, you'll see a video that explains these terms through visual cues. It will become much more intuitive. Neural networks can solve classification problems. It can also make predictions about target variables as interval or continuous variables. So neural networks are very versatile in terms of solving problems. The downside of neural network is because it's so complex, the numbers of the hidden neurons and the connections change, and there are so many of them, it becomes untractable. Therefore, although the results are beautiful, you have prediction results, you have accuracy margins that are smaller than 1%. That's far better than human errors. But if you try to explain how the neural networks are making prediction decisions, you are faced with an unbeatable mountain. It's really hard to crack open what is happening inside the neural networks. So that's why it says it's opaque. It's a black box. And that's why scientists and researchers are trying to push really hard for this explainable AI in trying to invent techniques that can crack open what's inside a workable neural network model that is proven to be making highly accurate predictions, but hard to know what's inside. Model is quite complex. You can keep adding layers, and also you can keep expanding the number of hidden units. You can put as much as 500 in other computer package. You can also train the network for multiple rounds. It will make the model more accurate in predicting the values in the training data set. It does become overfitting fairly quickly. And the number of input variable spaces also increase the complexity of the model. Model selection then becomes a problem. When you have a powerful model that is able to soak up all the nuances and variances of the data, when is the optimal time that you make the model to stop? You do need to select in a model that performs well enough in the training process. Model selection criteria based on the validation data set. So far in the semester, I've always emphasized that when you train a model, you rely on the training set error rate in order to keep pushing the model. But when you compare and try to select the best model, you make use of the validation data set. The selection of the criteria depends on the kind of task that you're performing. If it's a classification problem, misclassification rate will be perhaps the best choice. But if the prediction is about an interval variable, then average square error. Profit loss involves the decision weights and decision making, which is adding one more layer of complexity here. We'll talk about decision weights in the model evaluation week. The input variables do need to be normalized or standardized in order for the model to perform stably. Although there are two ways to standardize the data, there is a z-score standardization or a min-max standardization. The min-max would be preferred for reasons that will become clear when I introduce the video, and that you guys watch the video, you'll see the values inside the neural network after each activation function. It is kept in 0 and 1. So that's why the input variable better be kept between 0 and 1. That's when the min-max standardization becomes useful. To deal with a skewed distribution, as I talked about in the first video, you will make use of the log transformation, but it's not always required, and it's not always even optimal to do that. So my suggestion would be, when you have skewed input variables, you should try both approaches. One is apply transformation and use logarithm transformation, fix the skewed distribution of those variables. And also on the side, you do another version of the model training while you keep the original distribution of skewed variable, and you compare the model, because the only thing that's different is the input variable logarithm transformation. You can empirically see which approach is better for your specific case. The benefits of taking log transformation machine learning does depend on each case specifically, so there's no universal guidance to be provided here. If there are erroneous values, replace or imputation would be a better term to say. As a result of the erroneous values, you first replace the erroneous values, and then you will impute the values with imputation methods. I just talked about this. With categorical variables, because their labels are meaningless, let's say gender is a special case of categorical variable. It's a binary variable that has only 2 labels. Labels do not take values, so you can assign 0, 1 flag values to them. Typically, you would have k minus 1 number of labels. K is a number of discrete labels. If there are only 2 discrete labels, you will only create 1 indicator variable. In the case of gender, k minus 1 is 1 dummy variable to indicate whether the case is a male or a female. And you can name that variable specifically using the gender of the label that you assign, value of 1. For instance, if the case is female and you assign female of label 1, the variable will take 1. If the case is male, the variable will take value of 0, indicating that this observation is not a female but a male. Now it's time for me to introduce the video. This video is already uploaded to Blackboard. In the video, I would like you to specifically focus on these terms. At 2 minutes 25 seconds, about for 1 minute or so, it will talk about what is gradient descent. Gradient descent is the backbone of the optimization process of neural network in trying to back-propagate the errors and try to improve and optimize the coefficients of the neural network. Coefficients that I mentioned, those betas and those b's. Gradient descent gives computer the power to improve them bit by bit, iteration by iteration. After you have learned about gradient descent, it will talk about neural network at a higher level picture, and then it will talk about several things specifically. First thing it talks about is minimizing error. How does it specifically do with gradient descent in minimize or reduce the error and adjust coefficients? After you have a better version of coefficients with the input data, how does it forward propagate the information through the layers, and what does it mean by probability and activation functions? After activation, you have a neuron. Information will keep fed forward, layer through layer, a neuron through a neuron. But what does each of the neuron mean? Another myth here is that neural network is probably one of the best nonlinear models that can figure out nonlinear relationships. But all of the the smaller components of the neural network can be seen as mini regression models. But the regression models are quite linear. Even logistic regression, there's only one step that transforms linear to nonlinear. How so is it possible that neural network models can perform nonlinear predictions so well by using a bunch of linear models? So at this part of the video, it will talk about how it leverages each of the neurons to put things together and make excellent predictions. And so it will finish off by putting everything together and give you some examples. I hope that you will make very good use of this video together with reading the book. It will help you get a deeper understanding of how neural networks work. But however, do read the book. understand those basic concepts, follow the book and go through how does forward feeding and backward propagation works by using some of the example numbers inside the textbook. It does a very good job in illustrating through text how the information is transferred inside the neural network. That's only after you have read the book and be familiar with those concepts, and then you look at the video here, then you will be able to understand, oh, in a higher picture, how does it do and how do all the components put together. Alright, this will conclude the first part of the neural network lecture. I hope you enjoyed this video. I'll see you soon.